Have you ever looked up at Venus, our so-called sister planet, and just wondered, what went wrong? Seriously, let's get into it, because the answer reveals something absolutely profound, not just about Venus, but about our own home. We're going to tackle this great twin planet paradox, why one planet, Earth, cracked its surface into these constantly moving plates, while the other got stuck with a solid, stagnant lid.
And here's the wild part. They didn't start out different at all. Billions of years ago, Earth and Venus, they were basically identical twins. We're talking same size, made of all the same cosmic stuff, and both were just incredibly hot. They were born from the exact same cloth, with what you'd think would be identical futures ahead of them. So that brings us right to the heart of the mystery, doesn't it? If they started out the same, how did Earth end up with this dynamic, life-giving engine of plate tectonics, while Venus just didn't? Why did its surface never, ever break? To figure that out, we've got to look under the hood at the engine itself. See, plate tectonics isn't a given. It's a super complex planetary process that has to be switched on. Think of it like a giant engine that isn't guaranteed to start, even if you have all the parts laid out. Now, a lot of people think that it's magma pushing up from below that shoves the continents around. And yeah, that happens, but it's actually a pretty weak force. The real powerhouse, the thing that's truly driving the whole show, is a process called slab pull. And this is the key to everything. So what is slab pull? It's actually beautiful, simple physics. When the edge of a tectonic plate cools off, it gets heavier and denser than the hot, gooey mantle underneath it. So gravity just takes over. That cold, heavy slab starts to sink, and it literally pulls the rest of the massive plate behind it, kind of like a tablecloth being yanked off a table. But for this engine to kick on, you need a very specific recipe. First off, the planet's crust, the lithosphere, has to get cold enough to actually become dense. Second, the plates have to be strong enough to hang together while they're being pulled. If they're too weak, they'll just rip apart. And third, the mantle has to be cool enough for that sinking slab to actually be heavier in comparison. And here's the big twist in the story. Back in their super hot youths, neither Earth nor Venus had any of these conditions. Nope. Both had weak crusts and blazing hot mantles, so the slab pull engine was switched off on both planets. The real story isn't about how they started, it's about what happened next that sent them down two totally different roads. So, what was the game changer? What was the one ingredient that Earth had and Venus lost? It all comes down to one thing: water. We're talking liquid water, covering the planet in huge oceans. It turns out that's the quiet, unassuming deal-breaker in the fate of a world. See, water does three incredibly important jobs for tectonics. One, it gets into the rocks and weakens them, which allows them to crack and form these nice, clean plate boundaries. Two, our oceans act as this ridiculously efficient cooling system, just pulling heat out of the crust, making it cold and dense, which is perfect for slab pull. And three, it basically acts as a lubricant for the sinking slabs, helping them slide down into the mantle way more easily. And Venus, it had none of that. With surface temperatures that can melt lead, any water it might have had just boiled away into space ages ago. So without oceans, it had no real way to cool its crust down. Its lithosphere just stayed hot, weak, and kind of fluffy, the total opposite of what you need for slab pull. And this quote just nails the problem. As the source material puts it, even if a piece of Venus's crust wanted to sink, the system couldn't support it. The crust was just too mushy to form a solid plate. The whole process would have just fizzled out before it could even get started. So what happens when that tectonic engine never roars to life? Well, you get what geologists call a stagnant-lid planet. The whole surface is just one single, unbroken shell that just sits there trapping all the planet's heat from the inside. And this chart just lays out the difference perfectly. On the Earth side, you've got this steady, continuous release of heat through our plate boundaries. But then you look at Venus, it holds it in, and holds it in, and holds it in, until bam, catastrophic planet-wide volcanic meltdowns. Our tectonics are organized, self-sustaining. Venus's are just chaotic and messy. So here's the bottom line. Where Earth has a steady thermostat, Venus has a pressure cooker. It stores up its internal heat for maybe hundreds of millions of years, and then just dumps it all at once in these violent, world-changing events. It's actually why the surface of Venus looks surprisingly young. It gets a complete, fiery makeover every now and then. Oh, I love this analogy from the source material. It's just so perfect. Think about it like this. Early Earth and Venus were both like hot porridge. Earth, because it had oceans, cooled down and formed a skin on top, kind of like cold, cracked oatmeal. You can grab a piece of that oatmeal crust and pull it, right? But Venus, it just stayed as hot porridge. Now, you try pulling a solid slab out of warm porridge. You can't do it. It just flows back together. You know, this whole story, it leads us to a really profound, kind of humbling conclusion. We tend to think of Earth's geology, with its continents and oceans, as, well, normal. We think it's the default for a rocky planet. But the evidence from our very own sister planet tells us the exact opposite. Earth is the weird one.
Seriously, just let that sink in for a second. Plate tectonics is not the default setting. It is the exception to the rule. Most rocky planets out there in the universe probably look a lot more like Venus or Mars, these stagnant-lid worlds, than they do like Earth. Our planet's dynamic geology, this constant churning, it isn't some final evolutionary destination. It's a temporary and really fragile state of being that can only exist when a whole bunch of conditions line up just perfectly. It's an incredibly delicate balancing act. For plate tectonics to actually work, a planet has to be in this really narrow tectonic window. The temperature has to be just right, not too hot, not too cold. The crust has to be just strong enough. The density difference between the crust and the mantle has to be perfect. And of course, you need stuff like water to be around. If you miss any one of those, the window slams shut. So you see, Earth didn't achieve plate tectonics because it was special. It was more like an accident of timing and pure circumstance. Our planet just happened to be in the right place at the right time with just the right amount of water on its surface to just kind of stumble into this incredibly rare geological state. And this really is the final mind-bending takeaway. This dynamic, living world that we take for granted, it's not Earth's permanent identity. It's just a phase. It's a phase our planet is going through right now. It had a different phase before this, and it will have a different one long after we're gone. Which, of course, leaves us with one last fascinating question to chew on. As our planet continues to cool down over billions of years, its internal engine is going to slow. That tectonic window will eventually close for us, too. And one day, will Earth stumble out of this dynamic phase and become a stagnant-lid planet once more? Will it, in its very old age, finally come to resemble the sister that it left behind so long ago?